Now let's do an example of using the first and second derivative tests to get information about the behavior to analyze this particular function. Okay, so if I didn't have any way to actually map this out on a calculator or computer, I could at least get some general ideas of what the function, how it may behave. Okay, so let's go ahead first and look for the local mins and maxes. So local extrema. Okay, that's extrema again is plural for maxes and mins. All right, so what I'm going to do is use the first derivative test to find out where those values are, the local max and local mins of this function, and then the second derivative test will tell me the concavity of the function. Okay, so the first derivative, so when I take the first derivative, I take the derivative of this function, and I get 1 minus 3x squared. Okay, in order to find the critical values of this function, remember that what I do is I solve this equation. So I solve for where f prime of x is equal to 0. Now, notice that I'm ignoring the fact that critical values also occur where the derivative does not exist. And I'm doing that because I look at the original function, and I know that this is a polynomial, which is continuous on its entire domain, and in fact, it's differentiable on its entire domain. We know that because it's continuous on its whole domain. Okay? And even when I take the derivative of this function, I notice that there is no point that I cannot put into this function. In other words, the domain is all real numbers, the domain of the derivative. Okay? So there's no places where the derivative does not exist. I just know that by looking at the original function. Okay, so I know that the only places where critical values will occur are places where the derivative is equal to 0. Okay, because this is a perfectly smooth function. So I need to solve this equation for x. So when I do that, I write down this same equation, 1 minus 3x squared, set it equal to 0, and solve for my x values. These are x values for which the function is transitioning from going up to going down, or from going down to going up. Okay? So when I do that, I now have 3x squared is equal to 1, right? I just added 3x squared to both sides. And I solve. X squared is equal to 1/3. Therefore, x must be plus or minus 1 over root 3. Right? Remember, when you have a square, that means I'm going to have two solutions in general. Just take the square root. So it's plus or minus 1 over root 3 would satisfy this equation. So I have two solutions, two critical values. So C1 is at minus 1 over root 3, and C2 is at positive 1 over root 3. These, again, are the critical values, and they solve this equation. Okay, they're places where the function is transitioning, again. I just have to know what they are, whether they're maxes or mins. Okay, to do that, and in fact, not only whether they're maxes or mins, but whether they truly are places that are maxes or mins. Okay, maybe they're not. So what I need to do is actually use invoke the first derivative test to actually test these values to find out whether they're local max or min, or in fact whether they're min or max at all. Okay, but these are at least candidate places for where the function may have a minimum or may have a maximum locally. And by the way, even before I go any further, I can tell you already that this function certainly has no absolute maximum and has no absolute minimum, because whenever I don't tell you what the domain is of this function, we just assume that it's all real numbers. And certainly this function is continuous over the whole domain. It's a polynomial after all. And also I know that in fact there is no absolute maximum or minimum, right? We can keep plugging very big numbers into this function or very small numbers. So all I'm looking for really is local extrema. So that's something you keep in mind as well when you first look at a problem. So now that we've found these two critical values, again, I'm going to invoke the first derivative test to determine whether or not these are mins or maxes. So let's do it. So the first derivative test tells me, and I'm going to draw my number line here. So here's my C1, which is minus 1 over root 3. My C2 is positive 1 over root 3. And these are my x values. So remember, the first derivative test tells me that if the first derivative is positive for some x value, that implies that the function is increasing. Okay? because the slope lines are positive, the function is going up. And if the first derivative is negative, for the same reason, if the slopes are going down, the slope lines are down, the function actually is decreasing. Okay, so what I need to do is determine the sign of the derivative as a function to know what the function is doing before and after these critical values. Okay, so my first derivative is this. It's 1 minus 3x squared. I already have it written. And what I need to do is find some test values. Okay, so some test x values. So I'm looking for some x value that is before, it's over in this region in the domain of x, or the domain of the function, I should say. Okay, so something before 1 over root 3 is something like, we could take a minus 1, right? Because minus 1 is definitely going to be over on this side. So I'm just going to take minus 1. It's some x value over here. And I'm going to plug it into this function to see what the sign is. If I plug negative 1 in, so f derivative at negative 1 is, just put it into this particular function. I get 1 minus 3 times negative 1 squared. That's 1 minus, well, negative 1 squared is a positive 1, so this is 1 minus 3. And that's going to be negative. Okay, I don't care what it really is. It turns out to be negative 2. All that really matters is that it's negative. So in fact, it's negative. And again, I'm going to write f prime of x just to remind you that this is the sign of the first derivative. I've plugged some test value in before this critical value. Because remember, critical values are just x values. They're just points in the domain of the function. Okay, I get something negative. Now in between, choose an easy value. How about 0? 0 is an easy one. So if I plug 0, because 0 is certainly in between negative 1 over root 3 and positive 1 over root 3, right? So I plugged in over here, I plugged in minus 1, I plugged in 0. Plugging in 0 into this function, I just get that's equal to 1, right? It's pretty easy, right? It's positive, and all I care is that it's positive. Now, the key thing here, and one thing that you may not see right away, is that since these are critical values, the beautiful thing about the first derivative test is that I don't care what's happening, and I don't have to test any other value. I just have to test one value over here. I know the function is behaving the same way for every single x value before this critical value. So all I had to choose is just one of them. Negative 1 I chose. Same thing in between here. All I have to choose is one of them. And all I need to know is the behavior. That's it. I don't need to plug in other values. Just one value. And same thing over here. I'm going to plug in positive 1. When I plug in 1, you get f's derivative at 1 is going to be 1 minus 3 times positive 1 squared. That's going to be definitely negative again, right? That's going to be, again, negative 2. So it's negative. And I don't care about what the value is, just the sign. And again, this is the beautiful thing about the first derivative test. I don't have to plug in a bunch of numbers. I just have to plug 1, 2, 3 values into the first derivative as a function to find out the behavior of all the x values in between these values. Before this critical value, in between these two critical values, and after this critical value. Okay, that's the nice thing. It's a very powerful tool. And now, since I know this is true, I know that the function is going down over in this region. The function is going up in this region for all x values. And the function is again going down for all x values over here. Okay? So I could write this more clearly as this. I know the function is, f is decreasing on what intervals? Well, from negative infinity, all x values before this critical value, negative infinity, out to negative 1 over root 3. It's also decreasing, well, it's increasing, I should say first. It's increasing in between, so from minus 1 over root 3 to positive 1 over root 3. And again, it's decreasing between positive 1 over root 3 and infinity. Okay? That's very powerful because there are a lot of numbers, a lot of x values in the domain that I don't have to plug into the function. Automatically, I get all information about mins and maxes just by one simple test, and it's by using the derivative as a function. Very, very powerful information. Okay? So this means that, in fact, this function f has a local minimum at x is equal to a minus 1 over root 3, and a local max at the value x value, x is positive 1 over root 3. And I know that because the function is decreasing before this critical value, increasing after. So if a function is decreasing before, increasing after, it's a minimum. If it's increasing before but decreasing after, it's clearly a maximum. Okay? Let's draw sort of a cartoon picture of this function even before I use the second derivative as a test. Okay? Just to get an idea, using this information. Using this information, I know the function looks like this. Here's my critical value, negative 1 over root 3. Other critical value, positive 1 over root 3. Okay? I know the function is decreasing before that value. When it hits that value, it starts increasing again. And then after that value, it starts decreasing again. Okay? Again, it's decreasing before. It's increasing in between these two values. Right? Here's my one value, here's the other value. Okay, it's increasing in between, and then it's decreasing after. And if you drew slope lines, you'd see that the slope is certainly negative before this first critical value. It's positive in between the critical values, and all the slope lines are going to be negative after this particular critical value. Again, that's all the information I need without plugging in other values. Just 1 is all I need to plug in to my derivative as a function. Okay? And I know it has a local minimum here and a local maximum here. Okay? And to find out the location of this value, this has a coordinate of positive 1 over root 3, but the y value is f of 1 over root 3. So you plug 1 over root 3 into the original function to find out the f value, the y value. So that would be the highest this function gets, and the lowest this function gets is going to be f of negative 1 over root 3. So this is negative 1 over root 3, and f of negative 1 over root 3. Okay, is the location of these two values. Okay, that's the local minimum, local maximum value. Okay, you can go ahead and plug 1 over root 3 into the original function to find out what that value is. And you can plug in f of negative 1 over root 3, that particular critical value, into the original function to find out the lowest the function gets, at least in this local region. And we call these local mins and local maxes, again, because they occur in a local region, right? Meaning not for all of the x values, but for some of the x values, some kind of small region of the x values, some kind of interval of x values. Okay? Local min, local max. All right? So that's the first derivative as a test. Now let's move on to the second derivative as a test for this same function.